All right, so today we are going to continue on our conversation from last time when we discussed Bayes' theorem. We're going to get to that in a moment, but in order to really understand Bayes' theorem, we're going to talk in more detail about something that I mentioned last class, and that's conditionals. Or conditional probability. Conditional probability is simply assuming something happens. What is the chance something else will happen? To get a better idea on how we structure it, let's get some notation down. P A equals the probability of A. P A vertical line B equals the probability of A given B. For example, the probability that you brought an umbrella to school at any given day might be pretty low. The probability that you brought an umbrella to school at any given day, given there's a high chance that it will rain, is probably pretty high. In other words, it's different context. We did this last time when we said, assuming the person is a drug user, what's the chance the test will come back positive? It's very different than assuming the person is not a drug user, what's the chance the test will come back positive? It's all about these conditionals. The probability of A equals the probability of A, assuming B happens, times the probability that B happens. Makes sense, right? Chance that it rains, that's the probability you're throwing an umbrella given it rains. So the probability you bring an umbrella. Is that true though? We're not quite done yet. Let me call someone. David, if you win the lottery, would you be rich? Assuming that's a good size. But you have to play to win the lottery, right? Okay, so I could do it this way. I could say the probability that you are rich equals the probability that you are rich, assuming you play the lottery, right? Because this will obviously be the chance that you win, because you have to win in order to, you have to play in order to win, times the probability that you play. Do you play the lottery? No, you probably shouldn't. It's we discussed. You can do the math on it. The expected value of that is actually not very good. It's a negative. It's less than the cost of the ticket. Is this correct though? The chance that someone is rich is the chance, the probability that they become rich, assuming they play the lottery, times the probability that they play the lottery. Is that correct? So everyone who is rich is a lottery winner. What do you mean? Is that right? There's other ways to get rich. So we should also include this P tilde A, which is the probability not A, or of A not happening. That tilde, that little curvy line, that means not. Sometimes it's a little slash. There's other ways to become rich. Plus, so we can add a plus the probability of A, assuming B doesn't happen. times the probability that B doesn't happen. Well, I don't want to go all the way over because I want to use that in a second. So the probability of becoming rich, assuming you don't play the lottery, times the probability you don't play. That's a bit more complete. Any questions so far? These are the three notations that will be useful when we get to base there. Okay. Last week we talked about an interesting application of expected value just to cement our understanding of this, and that was prediction markets. So, this one. These are the prediction markets for who will win the 2020 presidential election. So, what is 33% of 33 cents on Donald Trump? What does that mean? Yeah, he has a 33% chance, right? We can interpret these because this ticket is worth $1 if he wins. So we can interpret these payments, these prices, as chances, as probabilities. What is the chance that Joe Biden will win? 13%. Or we can actually abbreviate that as 0.13, right? But included in this probability are two things. One, what is the chance that he will be the Democratic nominee? And two, what is the chance that he will win the presidency, assuming he's the Democratic nominee? Because there's two stages of elections. Everyone follow me? So maybe you're curious, who is a better presidential candidate? I think I actually want to erase most of this. Yeah, I'm going to erase this part because I want to work here. We need some space. I need a fair amount of space. Oops, I erased everything. Okay, good now. Who is a better presidential candidate? Biden or Sanders? Well, we can check the markets to see what the markets say. Because again, if you just say it, you're like, well, because I said so. But let's see what the data suggests. So this is chance to be president, and this is the chance to win. Chance to nominate. And I want to know, what is the chance? No, I didn't run out first. What is the chance to win, assuming they become the nominee? So what's the chance to win, assuming they become the nominee? Because I don't necessarily, because, you can argue that it looks like Biden is better, right, as a 13% chance versus a 12% chance, but maybe Biden has a higher chance because he's more likely to become the nominee, but he's not necessarily a better candidate. Maybe that's only so high for that. So, how do we figure this out? How do we figure out the conditional? Keeping in mind, oops, you know what I can do? I can call this. I don't like using P twice, but I guess I'll use P twice. The chance to become president equals the chance to become president, given you're the nominee, times the chance you're the nominee. Now, granted, I should also include a probability of the probability you become president, assuming you're not the nominee, but I'm not going to do that here. Why not? Yeah, I mean, you can be, but come on. Like, that doesn't happen ever. So we can safely say that while technically this is what we're working with, this is 0. So I'm going to ignore that. Okay. So the chance to be president looks like Biden has 13 cents, or a 13% chance. Sanders has a 12% chance. The chance to be the nominee, we also have that information right here. Who will win the 2020 Democratic presidential nomination? Looks like Sanders has an 18% chance. He's popular among the kids. And Biden is 16%. Oh, sorry, yeah, you're right. Thank you. The order got confused. And Biden is a 16% chance. So how would we figure out who is the better general election presidential candidate? How do we figure that out? Yeah, you can say your opinion, but I'm using market data, which is an amalgamation of lots of people's opinions, putting the money where their mouth is. Right? That's one of the advantages of prediction markets. So I want to start with this as my inputs, not necessarily making this a political discussion, just using the data. I want to figure out what this is. I know what this is. We can actually call this the chance to be president. PP. We got the data here. We know this, chance to be the nominee. PN. How would we figure out probability of P given N? Multiply? Look at this equation. I want to know what the conditional is. This is the conditional. I want to know what this is. I want to know, assuming someone is a nominee, what is the chance that they become president? Because that will tell me who's the better presidential candidate for the general election. Yeah? Yeah, I would divide, right? Multiply, I would divide. Get a little awkward. I'm using the P twice, but that's okay. So we can figure out who's the better presidential candidate. Take a moment to and appreciate the intuition for why this makes sense. Imagine Biden had a presidential probability of 0.16 of 16%, and this nominee was 0.16, 16%. In other words, the markets are saying the only reason why Biden wouldn't become president if he wasn't the nominee, because they would match. Right. So, what is 13 divided by 16? 0.8125. About an 81% chance. What is 0.12 divided by 0.18? Sorry, point what? 0.6. Oh yeah, because it'll be 2/3 naturally. Actually, according to the data, Biden is a stronger candidate. He's going to have a harder time becoming the nominee, but not much. Granted, a lot of things can change between then and now. This is still very early. It's like, what is it? It's like April 2017, 2018. Wait, 2018, yeah. It's April 2018. So we're still like over 2 years away. We're about 2 years away. I think 2 years from now, we'll have Democratic presidential nominee. But still, it's very early. A lot can happen in 2 years. Any questions? It's a fun way too, if you find two things unpredicted, or two probabilities, and one embodied in it has a conditional along with the other part, you can isolate the conditional by just doing some division. And no, any questions on this? Sure.
So now you know to a degree, right? The degree of how much better it is. Based on current. All right, let's do another example with conditionals just to sort of
Solidify our thinking on it. Consider Bob. Bob, let me try. I think I'm trying to. I don't want to use that example again. That was sort of awkward. It didn't quite work the way I wanted to. It's just weird. I might do it again. Fine, I'll just do it again. It's going to be imperfect because I'm going to think about earnings. It's all weird. It's awkward, but it will give us a nice framework. It is a bit intuitive, and that's kind of nice. Bob is thinking about going to college. He had some trouble when he was a high school student, so he's not sure that it's going to work out for him. He currently makes, we'll say $30,000 a year. He says to himself, however, if I go to school, I could make a lot more. I could more than double my salary, maybe, even if things go wrong well. At the same time, I recognize that because I had a hard time in high school, I don't really have a lot of background knowledge that's really helpful. I never developed those study habits that might be really helpful. I don't know necessarily how best I learn, but I'm also pretty motivated. So what probability do you think Bob has, assuming he goes back to school, what is the probability you think that he would get his degree, get his college degree? I should just say getting a bachelor's degree or getting a BA. I'm just saying getting a BA because I'm pretty good with sciences. What do you think that probability is? Think it's high? Think it's low? It's low. What would be low? Okay. We can do 40%. But if he gets a degree, he can make more money. Now, how much money he makes is dependent not just on how well he does in school, but also on market conditions. If the market is doing really well, if the economy is doing really well, he can make a lot. If the economy is doing really terribly, then he won't make very much at all. So, if he gets a degree, let's imagine that there is a 20% chance that the market is doing really well, and he'll make $80,000 a year. Let's imagine there's a 50% chance the market is doing pretty good, it's doing okay, and he'll make $60,000 a year. And let's imagine there's a 30% chance the market actually took a huge tumble, he might only $40,000 a year. Of course, there's also a chance he won't finish at all. That's a 60% chance. What does he lose? What happens if he doesn't get anything? Yeah, he loses money, but there's also the opportunity cost, right? He also isn't making money here. So, and if you want, we can make it simple and say he has a free ride. But at the very least, but only if he goes full-time and gives up his job. So if he goes full-time and gives up his job, how much money does he lose? But that's going to happen anyway, though, right? Oh, this is tricky. This is always hard. let's just say, I want to make it simple. So if he has a free ride, because he's going to give up the 30,000 regardless, right? He's going to give up 30,000 a year whether he succeeds or he doesn't succeed. So let's just, to make it simple, let's just say this is 0. Try to make it simple. You see why I was a little hesitant to use this, because there's a lot of like factors that go into it. Like this is 80,000 a year. This isn't a one-time payout. So the numbers I'm going to give you are deceptive, but they're just here to sort of try to master the idea of conditionals. What's the expected value of Bob's attempting to get a bachelor's degree? What's the expected value of that? I guess you could say like, you could say that the 60% chance he just goes back to his job. We can make that 30. Yeah, we can make that 30 just to make it interesting. Let's make it 30. Okay. Yeah. You could argue that maybe it should be lower because he left and came back, but how would we figure that out? So what are you doing?
You just multiply the probabilities times the value.
So we have a probability of 20, 50, and 30. And that is an 80,000, and a 60,000, and a 40,000. So that's all it is, and that's a third.
I didn't see you change that to 30.
Yeah.
We have to do 60%.
Okay.
Add that to because that's part of it.
Yeah, so that would be 18. How did you work the 40 in?
I did 40 times 20%,
Mhm.
which is 50%, 40 times 30%.
You know what Adam's doing. Why are you doing it that way? Why are you taking 40 times 0.2? Or 0.4 times 0.3? Why are you doing that? It's right, but why are you doing it that way?
Because it's like, because you have a 40% chance of getting to like that state and getting a degree, and then once you have the degree, you have a 20%.
Exactly. Because these are conditionals. Assuming you get a degree, this is the things that can happen. And this ends at 30. I should have said P equals. And P equals. So we have actually 4 different scenarios. And that would be 0.08 times 80,000. 0.5 times 0.4 is, of course, 0.2 times 60,000. 0.3 times 0.4 is 0.12 times 40,000. And then 0.6 times nothing is 30,000. So these are the 4 different scenarios and the corresponding payoffs. What does this end up being? Yeah, so what is this? This is, I think it's 60, does it add up to 1,600?
No, that one.
Okay. We'll do 1.6K. That becomes, 12K. Let's see, we got 4.8K, right? Yeah, so 4.8K, right? And then 18K. This is not looking very good. And then we just do some addition, which I don't feel like doing right now, so someone can do it for me. I mean, I'm going to do it anyway. That's 36.4. That's what I got. I want to double check my math.
I think the first one is wrong.
Did I do some? Ah, damn it. So which one's wrong? This one? Yeah, that's totally wrong. You're right. Oh my goodness. I'm gonna blame you.
Oh my god.
You told me 1.6. I trusted you.
Blame you.
Shut up. You're fair. I should have seen that. The A, the N, I don't know what I was thinking. Thank you. Oh great. Well, that's still pretty easy. That'll be 41.2K. There we go. That's better. I was like, that seems pretty low. That's better. Any questions? Yeah.
Why is it 0.08?
Because we took 0.4, so he has to complete, and then 0.2. So both of these things have to happen to get here. Just like we took, the probability that he finishes college times the probability that things turn out great, or the economy is great when he finishes college, assuming he finishes, equals the probability that things will be great and he gets the 80%, or he gets the 80,000. So that becomes 0.4 times 0.2 is 0.08. Any other questions? So that this gives you something to work with. Do you think that he should go to school if he gets a free ride? Really, I don't think so. Why? Why not? You said it was only 10,000. Why'd you say it was only 10,000?
Because it's everything on that.
Mm-hmm.
So you have to put in all the energy and time.
Yeah.
And schooling doesn't seem practically significant to put in all that work in school when he still has a chance to fail.
That's true. But it's worse than that, right? Because this is a 4-year degree. He's not giving up 30,000. He's giving up 120,000. Because he's going to give up it. He has to give this up for 4 years. So you could argue this is a terrible deal. I don't really know how we got a free ride, given he's only a 40% chance of completing. Must have been a killer essay. That said, of course, you could still argue it's worth it. Mm-hmm, yeah, because this is going to be over the course of many years, right? Is that what you're going to say, CJ? Yeah. But this again, but you can see how you can sort of frame a lot of your thinking about these sort of things. Again, I made up these probabilities. We rarely have these probabilities available to us, but by organizing these in conditionals and recognizing the different paths people can take, you can get some idea as to something to work with as far as if this is a good decision or not. And it forces you to think of all the different scenarios and not try to discount something. Just simply making this diagram, even if you don't attach exact probabilities to it, but just being able to map out all the different things that can happen is still very useful. It's kind of a version of, I think sometimes you see that if you're taking some management course or BSAB, the SWOT analysis. What is the SWOT analysis? Mm-hmm. So what do all those mean? So it's like we're going to try to do something. If we do it, what are the strengths of us doing it? So this is sort of the good interior stuff, interior to the company. The weaknesses of sometime within the company that can screw up. The opportunity is what sort of things for outside the company, what good things from outside the company we could do. Like if we engage in some new business, for example, maybe we could synergize with someone else. At the same time, there's threats. If we engage in this new business, maybe someone could attack us. This is a very common thing in business. I know it mostly because it was used once in Silicon Valley, a TV show on HBO, and it's a good show. That's how I remember everything. It's the first time I saw it. But this sort of framework helps you sort of organize all the different possibilities. Same story with this. Any questions? All right, well, now that we got some of our notation down and we got the intuition behind the conditional probabilities, let me give you Bayes' theorem, which is something I know you guys have been like really, really looking forward to. When are we going to get this damn equation? It's taking forever. But everything we've done is in preparation for this, the notation, the stuff that we did last class. In fact, as a sort of a guide, let's recall what we set up last time. What is the probability that someone uses drugs? What did we do that class? Remember? Exactly, 1% or 0.01 chance. What was the sensitivity of our test? %. And what is our specificity? It was 90%. Do you remember the probability that someone uses drugs assuming the test comes back positive? Do you remember what that result was? .008. No. 0.0748. Okay, it wasn't .008. 0.008 was the probability that we would get a true positive. Well, what we did last time when we took, here's the probability that we get a positive result, and then here's the probability of a true positive result, so the true positive divided by the positives in general, was Bayes' theorem, which is this right here. I think that my marker is dying on me. This deserves its own big talk. It is the probability. So the probability of A, assuming B happens, equals the probability of B, assuming A happens, times the probability that A happened, divided by the probability of B over A times the probability of A. So it's the same thing again here, plus, of course, B can happen some other ways, just like there's multiple ways you can get rich. And by winning the lottery, you can get rich by not winning the lottery in some other way. There's a probability that some other way will happen, but that you don't, play the lottery. That was my lottery example was a little awkward because it's wasn't mutually exclusive. You can play the lottery and do something else, but it's a basic idea of what we're coming across. There are multiple ways, just like there are multiple ways to get a positive result. We can take this idea and do it here. So the probability of being a user, assuming your test came back positive, equals the probability that the test comes back positive, assuming you are a user, times the probability that you are a drug user. I don't know why I keep making these mute. There we go. Probability, test comes back positive, assuming you use drugs, times the probability that you use drugs, plus the probability, test comes back positive, assuming you don't use drugs. Oh, I'm sorry about that. I thought that you did. Probably you don't use drugs. So note how this is identical to this. I just swapped out U for A. So I swapped out I got rid of A and added U. I got rid of B and added the positive to reflect the test came back positive. And we can do that math right now. And you'll see the math that we did is identical to the math that we did last time. What is this part? What is the probability that the test comes back positive, assuming you use drugs?
Aiden, is the test right? Is the test correct?
No.
What do you mean? Assuming someone uses drugs, the test comes back positive. Is that a correct result?
Depends. Could be.
Well, they use drugs. The whole point was the test to see if someone uses drugs.
I guess it's right.
It's right. The whole point is the test, right? The whole point is to check. So is that sensitivity or specificity?
Specificity.
So what does specificity mean again?
Anyone? What does specificity mean?
Negative state.
Ability to detect the negative state. So what would the example of that be?
That would be finding the non-users testing positive.
Well, just it would be in this case.
Not non-users testing positive, but it would be non-users testing negative. The whole point is that the test is right. In this case, the test is right, but not because we correctly identify non-users, but because we correctly identify users. The probability of getting a positive result, assuming the subject uses drugs. So, what should this be?
What should that be? Well, what is so specificity? It measures the ability to detect the positive state. What is sensitive? I'm sorry, the negative state. What does sensitivity measure? Give it a hint. I mistakenly said it. Yes, Morales. Ability to detect positive state. Okay. So what should this be right here? What should the probability of a positive result, assuming the subject is a user of the drugs? No, so this is the opposite. This is the probability that someone is a user, assuming they test positive. I want the probability that someone is positive. Probability a test comes back positive, assuming someone's a user. I want the opposite of that. This is what we're trying to figure out. I'm trying to derive it right here. Yeah. 0.8 goes there. Why does 0.8 go there?
Because the sensitivity that you said is the ability to test positive. So if they're user, we're trying to figure out the test positive, that's sensitivity.
Exactly. Drug user walks in. Obviously, don't know they're a drug user because that's the whole point of the test is figure out who's doing it. Drug user walks in. I test the person. There's an 80% chance I will correctly identify them as a drug user because an 80% chance the test comes back positive. Remember, in both of these, they're measuring the chance the test is correct. This one is the chance the test is correct, assuming the person is a drug user. This one is the chance the test is correct, assuming that they are not a drug user. Or this could be like, we could test other things. We could say, if we're testing to see who is a terrorist or not, the chance the test will identify them as a terrorist, assuming they are terrorists. The chance the test will identify them as not a terrorist, assuming they are not a terrorist. Chance the test will identify the meat as bad, assuming it's bad. The chance the test will identify the meat as not bad, assuming it's not bad, etc., etc. Okay? Great. What's the probability that you're a drug user? 1%, right? So that's just PE right there. Note that this section is identical to this right here. Because one way to get a positive result is to do this. So we're just going to copy and paste that down there. Now the fun part. What is the chance the test comes back positive, assuming the person doesn't use drugs?
What is the probability that the test
Comes back positive, assuming the person doesn't use drugs.
What's the probability of?
Well, let me try this.
test can either be correct
Or it can be wrong. Let's say, oh, let's just call it incorrect, so it's measured.
and we could be working with a positive state. In this case, the person is a drug user, or a negative state. Or in this case, the person is not a drug user. What is the chance the test is correct, assuming that it's a positive state? 0.8, right? Because that's the sensitivity. What is the chance that it is correct, assuming it's a negative result? 0.9. So note, sensitivity and specificity are measuring how good the test is, measuring how often it's correct under these different circumstances. Positive state, negative state. This is what we're starting with. What is the chance it's incorrect, assuming it's a positive state? 0.2. And the chance that it is incorrect, assuming it's a negative state? 0.1. Is that better?
So, what is the chance that it is, so ask yourself, is this the correct result? Is this right here, a chance the test comes back positive, assuming the person is not a user? Is that a correct result? No, it is not a correct result. So that means it's either going to be this one or this one.
So does this reflect a negative state or a positive state?
Well, the result is positive, but I'm talking about the state. I'm talking about what we start with. It's negative. The person is not a drug user, but the test made a mistake and it thinks they are, right? I don't know when the results come back. I don't know which is a false positive, which is a true positive. I just know the result's positive. So, this would, of course, be, I already forgot what it was, 0.1. What's the probability of the non-user? 0.99.
But we can use these numbers. We can also put in this. We'll get a true positive. A true negative. We can get a false negative. Or a false positive. In other words. No, I found the chance of a true positive, the chance that someone walks into the positive drug user, and the chance to correctly identifies them as one. And I found the chance of a false positive. The chance that someone walked in and I mistakenly called them a drug user.
A true positive and the false positive. A little bit of word of caution. I am using the chance of getting a false positive in general interchangeably with this particular instances right here. This is just for describing it. But of course, you have to take this times the likelihood of a positive or negative state. You get something that will work. Okay. Now we just finished, and it's the math that you've seen before. 0, 0, 8, 0.10, so I got a little bit of a brain fart. 0, 8. Yeah, that's right. And you get that. Just like we did last time. So you see the connection between what we did last time and Bayes' theorem. I was preparing you for Bayes' theorem. But what we did last time is exactly the same thing. Think of all the different ways you get a positive result. In this case, it was a positive result because that's our condition. And then all the different ways that we focus on the positive result we care about. Any questions on this? Great.
Let's start with this. Now,
Excel does not have a built-in Bayes theorem function. I gotta warn you on that. So what I'm going to show you how to do is set up Excel in such a way that you can have it calculated for you, but you still have to understand Bayes theorem. Though I will say for the record on exams, I don't really care if you use the tree diagram that we talked about last time, or if you use Bayes theorem that we're doing now. You do have to understand Bayes' theorem, but you don't necessarily have to do it for a question like what is the likelihood of pursuing on drugs, assuming that they got test back positive. You don't have to know that. You don't have to like do it the same way. I don't care. So here's the setup that I have. Again, using the exact same numbers from before. Probability, actually we can probably call that PU, just like to make it symmetric. So, I have PU, probability that someone is a drug user, sensitivity is 0.8, specificity is 0.9. And I want to know this, the probability that someone uses the drugs, assuming the test comes back positive. Nope. I've been using this same example over and over again. I don't want you to think that's the only point of Bayes' rule. You can put in, what's the chance that someone is not a drug user, assuming the test comes back positive? Or you can do what we're going to do this right here. What is the chance that someone is a drug user, assuming the test comes back not positive? Or if you want, assuming the test comes back negative.
by the way, if you want to know how to do those vertical lines,
Because people had trouble with this last time.
it is just above the enter. So, like, you know, the key that gives you this. Well, if you hit shift, you hit that. And it looks like it's so dumb how
Do it on these things because sometimes it'll look like this. I don't know why it looks like this. It creates a solid line. For some reason, they make it look like a dotted line. I'm a little baffled by it. Does my computer have that? So my computer makes it a solid line. Maybe
Is that just a weird thing on this computer? Maybe it's really more. Nope, on your keyboards it's 2 dots. It's so strange. But you know, it's left to the bracket space. Underneath you have backspace. So now we're good. Does everyone have this? It takes a while, I know. What I'm going to do is I'm going to set up my numerator and denominator. I can do this divided by this. I'm going to some properties.
I'm also going to take this time to rewrite this in terms of this. Because again, it'll be our guide. It's literally what I just did. But one thing I learned, it's helpful to get lots of practice. U positive equals probability the test comes back positive, assuming they're a user, times the probability that they are a user, divided by the probability that the test comes back positive, assuming they're a user, times the probability that they are a user, plus the probability the test comes back positive, assuming that they are not a user, times the probability that they are not a user. So it's exactly the same thing we can do. Handwriting's worse, but same idea. So, numerator. What is the probability that the test comes back positive, assuming they are a user of the drugs? Michael. What time was that?
You asking for the numerator?
Yes. I'm asking for the first one number. I think he said it.
E1 times E2.
So we'll start with E2 as our first one. But that's our point that we've been working with. That's our sensitivity. That is, the result is positive. You know, I can put these numbers back if you want. Or we can put them back. Was a 0.8, 0.9, 0.2, 0.1. So test is correct, right? Result is positive. The user, the person uses drugs, and it's positive sig. The person uses drugs, so it's 0.8. So we'll just reference 0.8, and then as noted, we also multiply it by the chance that they are a drug user, which is PU. That's right there, just like it matches right here, just like before. Denominator. Appreciate that this part right here is the same as this part right here. And that's always going to be the case. Which means we can save ourselves some time and just do that again. And the interesting stuff. What's the probability that we will get a positive result assuming the person does not use drugs? So, Saturday. Is this the correct result?
Yes.
So the test came back positive, but the person doesn't use drugs. And you're like, I'm okay with that. Is that correct? If a person who isn't taking drugs gets a drug test, and the test comes back positive for drugs, was that test correct? No, it was not correct. So this is false in some way. Is it a false negative or is it a false positive?
False positive.
It's a false positive, right? In other words, they made a mistake, right? So the whole point of specificity is we are going to be able to, 90% of the time, if someone doesn't use drugs, we'll correctly identify them as a non-drug user. Which means 10% of the time, a non-drug user will be mistakenly called a drug user. 10% of the time, a non-drug user will get a positive result. That's this right here. So, we will use our number order operations. 1 minus these 3. Maybe to put it in parentheses because we don't want to add 1. We want to, because we're going to multiply this by something. So this is our 10%. Times, what is the chance of not being a drug user?
Point one. 0.99, how to find that?
Because there's 1% chance of negative, so 1 is.
So yeah, right, one minus here, because I might want to change some numbers around. And now, we got exactly the same thing. I converted 100%. Exactly the same thing. That's what we're working with. For those of you who didn't follow it, or those of you who maybe got lost a little bit. Maybe they went too fast. Did everyone get this?
Yeah, this was new.
U is the drug user. U is this person uses drugs.
Maybe I should place that from a U for a D. Maybe drug for drugs, I don't know. So what's the probability someone uses drugs, assuming the test comes back positive? It's 7.48% chance.
Any questions? So, what do you think would happen
To this number, if we increased the how common drug users are.
Again, what do you think would happen?
So which number?
To
This number right here.
If we increase how, we increase what?
so like let's imagine it's at 1% of people who use drugs. Imagine it's 20% of people who use drugs. What would happen to the reliability of our positive results?
Or could be anything.
Increase that number, the numerator would increase as well.
And notably too, we'll get fewer false positives. Why? We're less likely to get a false positive. Why is that?
Because we would multiply the 0.1, which is the, we multiply 0.1 times whatever the new percentage of drug users is, which would mean that it's a higher percentage.
Sure, so this is going to be larger. But also, this, all things being equal, will be smaller too, because this right now, this not U, probability not U, that's in 0.99. If I change it to 20%, that means it becomes 0.8.
So we're not only, in all likelihood, getting genuine users through the system when they test it, we're also less likely to get what we're going to mistake the full drug users. And indeed, if we make that 0.2, it's now a 2/3 chance that person actually uses drugs. It's a much, much higher.
And you can see that here, the difference between these two is now 0.08. It's much, much smaller.
Rather than before, where the difference was much larger. And the numerator was so small, right? A lot of it comes from the numerator. And you can fiddle around with this too, with 35, you can maybe up the specificity. And now it becomes much more, right? Look at how much I made that specificity.
99.99%. Now it actually means something, because we get so few false positives. So few false positives.
Well, often make it shitty. We don't want to do that. It doesn't change at all, right? That's exciting. That's what we're all basing it on. So, the thought process is if you play around with these numbers, you get a bit more intuition as to what these things represent and why these numbers come out the way they are.
In a couple of minutes, I want to do this line too. So what is the probability? So we know that if we get a positive result, the person probably doesn't use drugs. God, well, maybe if we get a negative result, maybe that's when they use drugs, right? What can we infer from a negative result? We know a positive result is basically useless.
It's a some information. It's not great. It's a some information. So what would be the negative one?
Well, I can change this. What is the chance that someone's a drug user, assuming the test comes back negative or not positive? What is the chance? Negative, negative, negative. What is the chance that the test comes back negative, assuming the person doesn't use drugs? Well, sorry, assuming the person does use drugs, what's the chance that we miss them? 0.2, right? We are false negative, 0.2. The person doesn't,
The person uses drugs, but we think they don't. What's the chance the person uses drugs? Oops, I'm sorry, I should be doing this way. 1 minus that, there we go. Times, what is the chance that they use drugs? That hasn't changed. Same thing, we're going to use that again.
what is the chance that the test comes back negative, assuming the person doesn't use drugs? Right. Exactly. We're using our
Specificity again. They don't use drugs. We are correctly identifying them as not using drugs. It has to be negative. Times, and this is the same. What's the chance that they don't use drugs in the first place? What's that? So we get it.
In other words, when the test comes back positive, I can't be like, oh, you definitely use drugs because this person probably doesn't use drugs. Like, there's only a 7.5% chance that they use drugs. But if the test comes back negative, I'm pretty confident I didn't miss anyone. There's a really small chance that I missed someone. Note that this went from a 1% chance, I don't know anything about you, so I guess there's a 1% chance you use drugs. You take your test comes back negative. Okay, that's a lot less than 1 now. Still not 0, but it's a lot less than 1. Again, it tells us how we update our expectations. Does anyone have any questions? So everyone knows this really well? Yes? All right, great. So I'm going to let you go for tonight. I'll see you next class.